a numerical linear algebra class in the curriculum someday. Anyway, okay. So for us in here today, we are talking about path integral, which means something new, I think, for most people. How many people in here even remember what a path integral is? Never seen a path integral before. That is not a physicist. Physicists have to do path integrals all day. All right. So let's talk about this. Half integral. Yeah, half integral. Okay. Oh, actually, the first thing I'm sorry. I lied to you. I lied. Because the first thing I wanted to do is I spent a bunch of time last time blathering on about non-concrete things. And I wanted to make sure I computed some examples of how to do change of variables first in a more sophisticated way than you may have seen in your earlier classes. And then we're going to talk about path integration. Okay. So some of these examples are actually they're tough. I totally did that on purpose. Okay. So the idea with change of variables, the last thing that we ended with, and I think that I sort of laid out in the video, was that you think about change of variables. It wasn't the video last time. We talked about the change of variables formula, and the change of variables formula says that if you have a transformation that takes a domain over here, D star, and T turns that into a domain over here by D, where T is a transformation, then the integral over D of f of x and y dx dy, this is one instantiation of f of x, y, dA, is equal to the double integral over D star of f of x of u and v, y of u and v, the absolute value of the Jacobian of x, y, backwards, times du dv. This was the change of variables formula, right? Change of variables formula basically gives you a way of moving from one type of variables to another type of variables by substitution. Okay, so in practice, how does this work? Right, and this is an abstract sort of tool right here. How do you actually use this in a real setting? And the idea is, well, suppose I just give you a problem to do. So, good one. There's the integral. And I've got to tell you what D is in order for this to make any sense, where D is enclosed by the curves y is equal to x over 2, y is equal to 0, and x plus y is equal to 1. So there's the problem. And I'm going to write down the region, and then I'm going to talk about like why you wouldn't want to try to solve it this way, right? Why you might actually go looking for a change of variables. Okay, so let's see. So y is equal to x over 2 looks like this. And y is equal to 0, that's down here. It looks like this. And x plus y is equal to 1 is a curve that cuts through like this. And so the region that we're looking at is this in here. So the region's not so bad this time. So sometimes you do a change of variables to change the region. And sometimes you do a change of variables to change the variables, right? In this particular example, I don't really want to integrate this with respect to x or y. I think that would be awful because I have a square root with fractions inside of them where I can't get rid of the x's with the y's, right? And I have no idea how to integrate that. Because I could try to use long division of polynomials, but I'm going to have some gnarly thing stuck inside of a square root, okay? So this is the original region D here. So the question becomes, is there any way that I can think of this, if I can think of x and y as functions of other variables u and v? Because if I could substitute this out, or if I could define new variables, if I could define some new variables, in terms of x and y. Anything you think jump to mind here? Like, what would you really hope, knowing this is a textbook problem, what would you really hope would be a change of variables that might work in this question? I am hoping beyond hope that I could turn the numerator of that thing into one variable and the denominator of it into another one. Because if it was just root u over v, that's really easy to work with, right? It just turns into a root u and a root u, a u to the 1/2 and a v to the -1/2. It's completely separable. Everything falls apart in that case. So when you're looking at a question like this and you're trying to decide what to do, usually your first move is to do the most naive thing possible. Either look at the region and figure out ways to make the region into straight lines, or look at the function and decide, boy, oh boy, it sure would be nice if that was a u and that was a v. That would be awesome if that was true. So let's just do that and see if it works. Let's let u be equal to x plus y, and let's let v be equal to x minus 2y. So that is, we're defining new variables in terms of these old ones right here. Okay, so question 1. I mean, that makes the integral really easy, right? I mean, I'm not going to change anything else. I know that the region is going to be different now because this imposes this change of variables. This is a change of variables, right? It changes out this region that was in terms of x, y into a new region in terms of u and v. So this region is going to be transformed into a new region, which I'll have to figure out what it is. But at the very least, that makes the integral and the whole point of trying this. And yes, this is hard to say there's an algorithm for. This is the sort of thing where you just try things. You know, even one of the most irritating things about calculus 2 is how much of it was. Well, you just try stuff, and if it doesn't work, you try something else, right? That's very much active in these sort of change of variables approaches. And many a research paper has been written by somebody who stumbled across the right change of variables. In many parts of math, the change of variables are unique, or not unique, they're sort of standard. Okay, that's a much easier integral to calculate if I could do it. But somehow, I'm going to have to account for the fact that this region changed shape. So what's the new region look like? Well, is this transformation linear? Sure. So for a linear transformation, what you should think is, okay, so I look at this and I say, well, to me, that looks like I took the matrix that I got UV by taking the matrix 1, 1, 1, minus 2 and multiplying it by the vector x, y. That's what that looks like to me, right? X plus y is u, and x minus 2y is v. Make sense? Hopefully. Okay. So if it's linear, all I care about is where the corners went. Lines map to lines. I just care where the corners go. If I can keep track of the corners of the region, I know exactly where the map, what happens to it. So let's actually compute that. What is, so let's define t of x and y equal to 1, 1, 1, minus 2 times x, y. So what's our new region look like? In fact, we don't even need that. Why am I putting this in matrix notation? I must be a glutton for punishment. So it's just x plus y, x minus 2y. T of 0, 0 is 0, 0, 0. T of 1, 0. 2, yeah, it's 2y. Just my sloppy writing. T of 1, 0. Where's that point? Do you not need what? We don't actually. We're going to use the matrix when we figure out the matrix is going to. We could do this with the matrix, but I'm going to save the matrix to figure out what the area change happened to be. So I'm going to remember that the determinant of this matrix is going to describe how much the area shifted from one to the other. Okay, that's why we recorded it. So not in this case, not for the actual transformation. We could just use the definition of the function instead, and it would be the same thing if I used the matrix. Now, to find this point of intersection, you guys saw the easy set of equations. X over 2 is equal to 1 minus x. I think you end up with xy 2/3, 1/3. Coordinates at that point are 2/3, 1/3. Where does that go? You add them, you get 1. And if you take that and subtract 2 of those, you get none. Well, that's nice. It's like this problem was written by a textbook author, so nice things happen. Because when you're done, you end up with a region where the old region looked like this in the variables x and y. And the new region, because this was linear, I know lines are going to map to lines with the linear transformation. This is why I'm like in the book, a lot of times what it'll do is it will write the coordinates of points on the lines and then transform the lines as well. But when the transformation is linear, lines map to lines. You don't actually need to do that. You just need to track where the coordinates go. So what do we get out? Well, 0, 0 went to 0, 0. And 1, 0 went to 1, 1. And 2, 3, 1, 3 went to 1, 0. 0, 1, 1. So there's the new region of integration. It's like this. This is when the variables u and v. Now, I forgot to do something when I set this up, right? I did not forget. This dA relationship right here is the last thing we're going to have to deal with, right? Because dA is going to involve the distortion factor that comes from this transformation. So I have not yet written down dx or dy or du or dv. To do that, I'm going to have to write, to get an expression for dA, I'm going to have to actually write down the transformation. Okay? So there's 2 things left to do. The first is write an integration statement that turns this into an iterated integral. And the second thing is to write down an expression for dA that relates dx, dy, which were my original variables, to du and dv, which are my resultant variables. Okay, so what's left to do? So we started with an expression that looked like this. dA was, well, the original expression was in dx and dy. So if x is in y, so do you guys remember the expression that relates these? It involves the Jacobian. Jacobian is running around here. You could actually compute this like this. In the xy case, we had a transformation that did what to area? Well, here we had a triangle that had area what? What's the area of this? This was 0, 1, 2/3, 1/3. What is the area of that triangle? One half times base times height. 1/2 times base times height. 1/3, 1/3, 2/3, which is 1/6. Is that okay? The area of the original domain was 1/6. The area of the final domain, this is a linear transformation, so I can do it this way. What was the distortion to the final domain? This is what? 1, 1, 1. Area was? So what was the distortion factor? 3. So du dv, the area in the du dv variables is equal to what times, so then it's a factor of 3 that relates these areas in the linear case, right? The reason that we're having to do this way and not just write the Jacobian down is because the transformation is actually pointing the wrong direction when we do this. Okay, so I'm trying to keep track of what the Jacobian is doing, and I'll be more clear about this. It involves the inverse of a matrix, or 1 over. But the idea is there's a multiplication of 3 here, which means if you go from the x and y variables to the u and v variables, you multiply by 3 in the area change, right? So that means if you went from the x and y variables to the du dv variables, that was a multiplication factor of 3. But if we're getting rid of the x's and y's and putting the uv's in their place, I can't use this expression. I need this one. Now, when you guys are doing du dx in the integral problems, and you always have to divide by the constant, the reason you're doing that is because you're actually using the inverse of the transformation to track the distortion. So we're treating this like a substitution problem, which means we used a transformation that basically went the wrong direction for this. We got this relationship using our transformation, but the substitution we want is to get the dx, dy out of there and get the du and the dv in. Does that make sense? So dA has to be calculated like this, right? Our area unit has to be calculated this way. Okay, so that gives us, now the only thing we haven't dealt with yet is how to do this with limits of integration. So now we're here. Now we can say that this is the double integral over d star of the square root of u over v times 1/3 du dv. The last thing we have to do is keep track of what happened to this domain. How do I integrate that with a, how am I going to integrate that? Well, this line right here has equation u equals v. That's pretty nice. So we could write the integral from 0 to u. So if I pick a u value, I integrate from 0 up this line, u equals v. So the v is given by the coordinate u. And then if I do all the u values from 0 to 1, then I'll have the whole region. So the integral from 0 to u of the integral from 0 to 1 of the square root of u over v times 1/3. This is a dv integral first and then a du integral second. And that's the reduction of the problem to an iterative integral. So these problems are long in this way, right? Because there's a lot of steps that you've got to keep track of. It's not just that this substitution. Like again, in the u substitution, there's always this distortion factor that comes from computing du in terms of dx. That's what this is doing here. We're computing du dv in terms of dx dy. Yep. So in that case, basically, if you couldn't compute the area directly, the relationship I'm trying to point to here is the relationship we already have, which is that du dv dv is equal to dx dy over du dv times dx dy. That thing was the matrix that we wrote down. And this Jacob, so the problem is we have this in the wrong direction because this is what I'm trying to substitute out. I need to put these in, but this is just some number, right? So you might have to invert this thing basically in order to do it on the other side. So these problems are more complicated than they look at first glance. In theory, you can do these sort of things. Almost always the reason they use linear transformations is because it's easy to go back. Or you use a standard coordinate change, like dx dy is equal to r dr d theta, which is the next thing we're going to do, which is a harder question because it actually requires that you're, well, let's finish this first. Can I leave this here? Is this okay to leave this here? Because this is the integral from 0 to 1 of the integral from 0 to u of root u times, let's write it like this, u to the 1/2, v to the -1/2. dv du. And that's actually pretty easy because first you just integrate that into a u to the 1/2 independently of this. And then you just have a really easy problem to integrate in u. So I would consider this to be something I hope I can just leave it at this point so I can move on to another example and don't have to walk through like calculus 2 integrals. If anybody does not see how to go any further than this here, let me know and I'll walk through the rest of the example on notes. Okay. Yep.
Did you ever find the determinant?
So the determinant of that matrix, let me explicitly connect that matrix back to what happened here. What is the determinant of this matrix? the determinant of 1, 1, 1 minus 2 is equal to minus 2 minus 1, which is minus 3. And so the absolute value of the determinant of A is equal to 3. That's what I computed right here. So my area, my change of area, where I saw it was a linear transformation, I computed the area distortion. It means that the area distortion is always the same everywhere. This is the determinant of the matrix. It also happens to be the Jacobian matrix for this particular transformation as well. But that's the Jacobian matrix that keeps track of X and Y variables changing into U and V variables. And that's why we had to use 1 over 3 instead of 3. 3 is the distortion factor that gets us from X and Y to U and V. But I want U and V to X and Y to make the formula work correctly. All right? No?
No.
Okay. So let me see if I can be more concrete. What does the formula say that you're allowed to do? If you have a double integral in one set of variables over some region, and you can write those variables in terms of different variables, f of x of u and v, y of u and v, determinant of x, y, d, u, v, u, right? That's the formula that we developed in class, yeah? Oh, there's absolute values. Okay, when I wrote this substitution down, what did I write? Did I write x as a function of u and v, or did I write u as a function of x and y? The second one, right? So the problem is this formula is set up the wrong direction, right? This formula is set up so that x and y were the original variables, and u and v were the. This one says, oh well, if you could find some variables, you could do this, right? If you could write x as a function of u and v, and you could write y as a function of u and v, you can do this translation right here. The problem is, by the nature of the substitution I set up, I have this built backwards. I have u as a function of x and y, and v as a function of x and y. So what I'm saying is, like, this matrix is the wrong. I can't do what I'm trying to do here.
How do you build it?
How do I build?
Like, I don't exactly understand where.
How I did this?
Yeah.
Oh, okay. So it's just so like the book actually just asserts that if you have a linear transformation like this, if you ever have anything that looks like u is equal to ax plus by and b is equal to cx plus dy, that you can think of this as being this particular matrix multiplication, because if you actually multiply AB times XY, you get AX plus BY and CX plus DY. It's just immediate. It's just a real quick. I shouldn't have been so glib about reading it off. But all I did was I said, well, 1, 1, 1 minus 2, which is the 1, 1, 1 minus 2 that I got there. Yep. Okay, I will put another example or two of this up on the page so you can see working through these things. Okay, I'm trying to give you one example so you've seen it once, and then I do another example written out all the way, where we work through it again, and then I'll give you some of these things to work through so you can get some practice doing it. Okay. Okay. Yeah, the issue again with all of this computation and trying to use this formula is that I did it backwards. Like, if I need a formula that takes x and y or u and v and turns it into x and y, this is a formula that takes in an x and y and spits out a u and v, which really means that I should be using the matrix A, B, C, D inverse UV is equal to XY. That will give me the translation that gets X and Y as functions of U and V. I just didn't want to work through the process of writing down a matrix inverse. Okay, these problems tend to be kind of hard not because any one step is hard, but because there's a lot of subtleties in making sure everything lines up correct. Here's an easier one, at least on paper. Okay. Somebody remind me what this translation is. So it's dA, if I go from Cartesian coordinates to polar coordinates, what goes over here? R, dr, d theta. I showed you guys geometrically why that happens, right? That's the thing where you look at the sector of a circle out here and you pretend it's a rectangle. Its dimensions are r d theta by dr, which is why you get that area translation. How does it show up in practice? Well, I'm going to give you a problem that is not nice. Yuck, you should say. I don't want to do that. You really want me to start off a problem with a trig substitution in variables x and y? That sucks. I don't want to do it. Right? If only there was a variable substitution that occurred to you. Like, for example, the book says, use polar substitution to make this into an easier integral. So, what does the polar substitution say? What's the relations that you have if you're going to do polar variables? Like, what do you know about x? What's the relation between x and y and r and theta? R squared is equal to, oh, look at that. That's just an r floating around down there. That'd be awesome. Great. What are the other relationships that might show up? X is equal to r cosine theta. Y is equal to r sine theta. Oh, but you guys are leaving off the best one. I'm actually going to not put it in terms of arctangent, but I'm going to write down that tan theta is equal to x, or sorry, y over x. The reason I don't want to arctangent is because I don't want to deal with the domain issues. Okay, so this family of substitutions is what you use when you're going back and forth with polar coordinates. Now, this problem looks like I'm insulting you with how easy it is. I mean, just look at how pathetic that is. Like, you just do a substitution, right? So let's do it. I promise I'm not insulting you. This problem is more complicated. So you look at this and you say to yourself, aha, an x squared plus y squared. I bet I could use a polar substitution to make that nice. So you do. Now, the first thing you do is you pretend for a second, oh, I have no idea what's going to happen to the region. Of course, if this was a u substitution in one variable, I could just compute the change of coordinates, but I can't do that because I got a two-dimensional input space. That's going to have to be transformed. So let's just ignore it for now. Just ignore it. It's going to be a double integral over some transformed region. But now the function's nice. dy dx gets replaced by r dr d theta. And the square root of x squared plus y squared gets replaced by the square root of x squared. Oh, this is the nicest function that's ever been integrated. Look at that, it's just r squared. And the square root of r squared, well, r is always positive, and the square root of r squared is r. This is r over r. This is just the double integral of our region of dr d theta. Wow. How nice my professor is to give me something, everything counts it on. And then you try to figure out what happened to the domain. Oh, man, okay. Well, here is now what you're faced with. How can you describe that region? This region right here. In fact, the first thing is, what region is this? You got two tasks here. What on earth is the domain that's described by this region? And then once you know what it is, you have to reparameterize it in polar variables. So I look at this, everything was easy until I had to deal with what the domain of integration was. So you should be able to read off what the domain of integration is just by looking at that. What are the possible x values that are being used here? 0 to 3 or 0 to x? 0 to 3, right? dx is the outside variable. Those are x values. Okay, so go from 0 to 3. And then for each given x value, what do the y values do? From 0 to, like if you were at 1, if you were at x is equal to 1, what y values would you travel through? From 0 to 1. If you were at 2, what y values would you travel through? 0 to 2. Oh, okay. It's this. It's a triangle that has y equals x on this side. And then the outside, the x values go from 0 to 3. What this is telling you, this is the hard part of these questions, is reconstructing the domain of integration from the limits that you see here. Okay. Okay. Now the part that's not going to be any fun happens. Okay, so anyway, the idea is that like this tells you for a fixed value of x, you travel from y equals 0 to y equals x. In fact, oftentimes it's actually easier to figure out what's going on if you write y equals x, x equals 0, x equals 3 in here, because this will tell you that you're integrating from 0 to the function y equals x, which is exactly what this triangle shape looks like. Okay, so there you go. There's a domain. Now, rebuild that domain in polar coordinates. You guys go ahead and tell me how to parameterize that domain in terms of polar coordinates, which is going to require that you remember how to write vertical lines in polar coordinates. I mean, I need to come up with an r and a theta to describe that region. I'll give you a hint though. What is the, the angle is easy. This right here was originally the line y equals x, right? So if you go from theta is equal to 0, what theta are you going to stop at? If that's the line y equals x, better be pi over 4, right? I mean, okay, sweet. Okay, that's the easy part. But for any fixed theta, you go from the origin, the pole, out to this line, right? Oh man, a vertical line, r is a function of theta. If only there was a way I could translate things from Cartesian coordinates into polar coordinates. What is the equation of this line right here? And just in regular old x and y variables. What line is that? Over here. X equals 3. Okay. X is equal to 3. Do you know an expression for x that involves r and theta? I do. R cosine theta is equal to 3. But I want to find r as a function of theta, right? Because I'm supposed to have a fixed angle theta, and then it tells me how far out to go to find the radius, right? From here to this line. So r is equal to 3. The injustice of the world that vertical lines in polar coordinates are secants. What did we do wrong? So that is the equation of a vertical line in polar coordinates. Just by translating that using the x is equal to r cosine theta formula, we get that this radius, considered as a radius here, that this radius point right here is theta, comma, 3 secant theta. So secants in polar coordinates translate into Euclidean vertical lines. So the hardest part of a polar question for most people is not in the substitutions, which are obvious usually, but in taking a domain in Cartesian coordinates. The Cartesian coordinate description of this is y is stuck between 0 and x runs between 0 and 3. That's the Cartesian description of that region. The polar description of the region is r runs between 0 and 3 times the secant of theta, and theta runs between 0 and pi over 4. This is the part that's hard, is recharacterizing not the function, but the domain, especially if the domain has straight lines on it, right? Okay.
For the 0 is less than equal to r is less than equal to 3.
3 secant. Okay. Now, if anybody has any questions about how we did this translation and why it works, like I want to make sure that we're clear about what's happening here. The point is that this line right here, this line that tells us what the this line here with this particular radius. Notice the radii are increasing as we go up here, right? Every angle you put in, the radius goes up because the radii are sweeping away from the pole as you go up. Imagine as the line keeps going up, the radius gets longer and longer and longer. What's the relationship? Well, this is the line x is equal to 3, which in polar coordinates turns into the line r is equal to 3 over cosine theta. That's where that bound came from. This tells me how to deal with it in X and Y coordinates. This tells me how to deal with it in R and theta coordinates. The same line, depending on the coordinate system. All right? So now I'm ready to solve the problem. After all this, if you've done it correctly and you're finished, you get something you can actually integrate. And it turns out to be the case that the integral from 0 to 3 of the integral from 0 to x of dy dx over the square root of x squared plus y squared in polar coordinates becomes the integral from 0 to pi over 4, the integral from 0 to 3 times the secant of theta of just dr d theta. Now, I have a quiz for you, real quick one, which is, I look at that and I think, I'm going to have to integrate secant. But every single person, it's not a secant cube, right? I mean, come on. It's not a secant cube, but it is a secant. Every single person in here is supposed to know what the integral of secant is. I'm going to remind you, I know you guys all know already. Everyone's just on the tip of their tongue, ready to just like throw their hands up in the air and tell me what the integral of secant is. How many people could actually do that right now? Oh, I want to hear your guess. Oh, that would be nice, but no. What do you think? Oh, you guys agree with each other. Okay, so by democracy rules, that must be the right answer. In fact, it is. That is the right answer. Okay, so yes, you are. It's a good idea to refresh yourselves with these basic things because a lot of these problems, notice this problem is about as easy a problem as you can make that has any meat to it at all, right? And the only meat here is this translation from Euclidean domains into polar domains, but it still is going to require at the end of the day that you remember this. Right? You should, I mean, this is considered to be one of the basic integrals you're supposed to know because it's one of the fundamental trig functions. Okay. What's the integral of cosecant?
Very similar.
Well, cosecants tend to be affiliated with cotangents, not cosecants, right? Or not tangents, yeah. Look it up. Did I already offer you guys the secant cube deal? Okay. Nobody took me up. Okay. So that's basically the story with change of variables, right? So what's the hard thing about change of variables? In the first case, the problem was not changing the domain, right? The change of variables is hard because of two things, right? So in the first case, we did the integral of the square root of x plus y over x minus 2y dx dy. In the first case, the problem was that the substitution, well, actually, in both cases, really, it was this change that was hard, right? Taking this, turning it into dA, and figuring out what it is in terms of du and dv. This was the hard part. Figuring out the substitution and then calculating what the area distortion had to be from one set of variables to the other. And the second question, the hard part turned out to be not the integral, certainly, but the fact that we're taking an integral in everything about this was easy. So in number two. Number one, what was hard was the transformation, actually discovering the substitution. Now I'll tell you, if I give you guys a transformation to do on a test, I will tell you what the transformation is. I'm not going to have you fumble around and try to figure out what the substitution has to be, right? I'll just tell you. For a problem like this one, I would have just told you to use u is equal to x plus y and v is equal to x minus 2y. Right, so the substitution is hard, tracking the transformation is hard, but the integral is easy. In this case, the domain transformation was pretty easy too. In this one, what was hard here was the domain, like figuring out what happened to the domain transformation was hard. And also, reading the original domain was hard. So, as an example of the way that like you have to be able to do this, you can imagine that if I just wrote some integral down and I said, draw a picture of the domain of integration, that's a really important skill to be able to have, right? Even if you don't do the integral, and many times people don't do integrals by hand, hardly any machine is going to tell you what the picture of the domain of the integral of the region of the domain of integration is, right? The region that's being integrated. It's happy to do the numbers for you. I mean, Wolfram Alpha is pretty good at this. But if I wrote down something like this, y dx, and I say, find the domain, draw a picture of it, because that's part of doing a change of variables or understanding what's going on with one of these integrals, then you need to be able to say to yourself, okay, what's actually happening here? I'm doing an integral where the y values are going between minus x squared and x squared, and the x values are running from -1 to 1, which means you should be able to write down that you're looking at something that looks like, oh, this is a terrible example because these will actually intersect each other. No, it's okay. It's okay. This. And so it's between them. It's from minus x squared to x squared, which means you're looking at this region. -1 to 1. That's an important skill when you're looking at one of these integrals, to be able to reconstruct this picture from what you see up here. Okay. So this is another one. I will not give you one of these where you have to do this for like more than sort of these basic functions, like quadratics and lines and things like that we've seen, but you still need to be able to do it. Yep.
We need to be able to do that for something like free secant data. Like, I honestly don't know what that looks like.
So, well, I mean, a free secant data, if I gave you something in, no.
Okay.
No, in the forward direction, it's okay, because if I tell you that you start with x equals 3, you can derive the fact that that line corresponds to r is equal to 3 secant theta. Mm-hmm. Most of you don't work in polar coordinates enough where you're going to have it in your heads that when you see a secant theta, that's a Euclidean straight line, right? You're just not going to know that.
Yeah.
So. Okay, so let's finish up today by at least introducing the idea of, so I guess before I do that, I will say these notes are posted, those examples are worked through to the point that I did. You notice I didn't finish the integrals because after that point, the integrals are just basically grinding past that point. If you need practice with the integration, you should, you should do those, but don't get buried down in some integral that you can't do, right? Get it to the point where you can do it, where you have an integral that you know you can do. I will not give you so many of those that you need to worry about doing like 52 integrals, but I need to remind you guys that integration exists and how to do it. Okay, so practice these, okay? And if you have trouble with the techniques, please let me know so I can do some more examples so you can follow step by step what's happening. Last thing I'll talk about today is I'm going to at least get you started. I want you to start working your way through at least the beginning. I know Collie can be hard to read, but a digest of what's happening in 6.1. The first thing, this is going to be about line integration. So line integration means integration along a path. So what we mean is we have some path, x of t. X of t is required to be a C1 path. And the idea is, so we'll start by thinking about what it would mean to be a scalar line integral. So you have some path, x a to x of b, running around in a domain, right? So this is a path in R2. And what you think of is, okay, suppose you had some function f that was a scalar field. So f is a scalar field. And by a scalar field, what I mean is to each point, f assigns a number. Every x and y that you feed f, a number comes out, right? F of any x and y is equal to I'm going to say, I mean, we'll call it Z, but I don't want you to think about this as a surface. I want you to think about it as like a temperature being attached, right? It's a number. So what does F do to a path? Well, one thing you can think about what it does, if you cut the path into a bunch of little pieces, and I want to figure out the average value of F, or the total value of F along the path. One thing you can think is, if I'm going to integrate, I have to come up with a Riemann sum to work with, right? So if I pick some representative point in each piece of the path, and I call that point, say, TK star, the point corresponding to X of TK star, right? There's some time TK, I evaluate X at TK star, and what I get is, that tells me the point, and what F does is F looks at that and says, I'm going to give that point a value. I'm anthropomorphizing the function. So F says, aha, to you, I assign the value F of X of TK star. That's what that chunk of the curve is worth. That chunk of the curve is worth that much. And every chunk of the curve has a value attached to it. The point is to say, how much is the whole path doing, right? What is F doing across the whole path? If you want, you can think about this as a height. And what we're saying is, okay, I've got some height attached here. What's the total height that piles up? What's the area that of this two-dimensional shape that sits on top of this path? This is why I hate this analogy, by the way. But maybe I'll try to draw this. So in 3 dimensions, it would look sort of like this. And you can think about what F is doing is it's sort of attaching, man, this is hard to do. You can imagine that what F does, this is the same picture, right? The idea is that this is X and this is F of X. F assigns on top of the curve, it puts heights up here. And you can imagine that as you wiggle the path around, you get this sort of sheet coming out. And I want to know what the area of the sheet is. That's a standard thing to do with the integrals, right? Area like corresponds to things like displacement if this was velocity, for example. Or if this was charge density, then you would be adding these things up to get total charge, right? If this was a density function, then density times length gives you some quantity like charge, and you could add up the total charge. There's a lot of ways to think about what a path integral is doing. So to each point in the path, F assigns a value, thought of as a height, or thought of as like a mass, if you like, or a charge. And what I want to do is I want to add up the total value of F that it contributes across the whole path. Okay? So if you think about F as a density, or you think about it as a height, then you can think about what is the area of this, or what is the density of this. And it turns out that the thing that you want to do is add up the height at each of these points inside each chunk, and then multiply it by the base of the rectangle. But what is the base of the rectangle this time? We have a name for little tiny pieces of a path. What was the letter we used to mean path, like path length? We use S, right? S meant little changes in path, right? S is like little distances along an arc. So I want to put a delta SK here. This is the height of the function on a particular piece of the curve, and this is the length of that little piece of curve. You can think about that's like all you're doing is you're figuring out the area of this rectangle, right? This rectangle has sort of base delta SK and height given by F of X of T TK star. So we'll get back to this next time, but the idea is if this represented a density and this represented a length, then this gets you something like charge or mass, and you can add it up to get the total of that thing. And this kind of Riemann sum setup is going to get us a notion of what's called the scalar path integral. We'll talk about that next time. All right.
Thank you. Do we have this back